The last class we were talking about activity diagrams. An activity diagram is essentially a flow chart showing flow of control from activity to activity, and it's part of a behavioral modeling process. It is used to model workflow as well as program details. So these are the different notations that are used in activity diagrams. This sort of rectangle represents activity states, this represents action states, this arrow represents input event, this arrow represents output event, and this sort of thing represents object flow states. Fork and join are represented by solid thick lines, transitions by arrows, control flow by dashed arrows, and branch or merge by diamonds. We also showed how fork and join can be represented in this sort of flow chart, and branching is used by this sort of diamonds, and this is branching and this is merging. And we also showed an example of signal sending and receiving. So we will finish this topic today by looking at two other concepts, object flows and swim lanes. Sometimes objects are involved in the flow of control in an activity diagram. Objects are involved in the flow of control associated with an activity diagram. So, for example, the vocabulary of the problem space may include order and bill, and instances of these two classes will consist of this object flow between the different states. And you can specify the things that are involved in an activity diagram by placing these objects, which are produced as a result of certain activities, these objects are placed in the diagram and connected using a dependency to the activity or transition that creates, destroys, or modifies them. An object flow represents the participation of an object in the flow of control. Let us see an example of an object flow. This example illustrates a process and activity diagram involving customer and sales. So this starts with a request by the customer, and there is a fork here, and as a result of it, an order object is generated, and the status of the order object is now placed, and the customer also initiates the pay process. The order object is fed to the take order action state, and then this pay and a filled order is joined here at this juncture, and then the deliver order action state goes to the deliver order action state, and deliver order deals with the order whose status is delivered, and on this side we have order which is entered and which is fed to the fill order action state, and the fill order, there is a relationship from fill order to deliver order, and the order delivered is fed to collect order, and this is the end of the activity diagram. So this order is the object which is flowing and which is used by the different action states or activity states in this activity diagram, and the status of the order is put here. So we have order placed, order filled, order entered, order delivered. The next concept that we will consider is the concept of swim lanes. Sometimes when you are modeling workflows of business processes, you will find it useful to partition the activity states on an activity diagram into groups, and each of these groups represents the business organization which is responsible for these groups. Each group represents the business organization responsible for these activities. And these groups are called swim lanes. Each swim lane represents a responsibility which is a part of the overall activity of the activity diagram and which is handled by a particular group. So let us see an example of a swim lane. So here we have an activity diagram where the customer, sales and stock room are the three swim lanes. In customer, there's an activity state request product followed by a fork, and sales, the take order activity takes place in the sales group and pay by the customer. And fill order is done in the stock room, and there's a join here from pay and fill order, followed by deliver order which takes place in sales, and collect order takes place in the customer. And this is the end of the activity diagram. So we have here 6 activity states: request product, pay, collect order, take order, deliver order, fill order. Out of these, request product, pay and collect order take place in the customer end. Take order and deliver order take place in sales, and fill order take place in this stock room. And we have organized this into 3 swim lanes. So with this we will finish behavioral modeling. And so we have talked about structural modeling and behavioral modeling and how they are represented in UML in various forms of diagrams. Next, we take up the implementation aspect of the system or architectural modeling. There are 2 implementation diagrams in UML, and both are concerned with the physical system organization. And these 2 implementation diagrams are component diagram and deployment diagram. Number 1, component diagram. Number 2, deployment diagram. They deal with the physical details of the system organization. So before we come to component diagrams and deployment diagrams, we would like to give certain definitions of nodes, components and other things, and then we will come to how to get these diagrams. First, we will come to the definition of components. What is a component? A component is a physical and replaceable part component is a physical and replaceable part of a system that conforms to and provides the realization of a set of interfaces. We use components to model physical things that reside inside nodes. Use components to model physical things that reside on a node. For example, executables, libraries, tables, files, and documents. So a component actually represents a physical packaging of logical elements. So it represents some physical packaging of logical elements such as classes, interfaces, as well as collaborations. For example, let us show the notation of components. We draw components in this fashion. We give a box like this, and inside the box we write the name of the component. This particular component is a library, and its name is kernel.dll. We can specify a component either only by its name, or we can also give the details. For example, we have here a component whose name is fraudagent.dll, and we provide some more detail by saying that the component realizes this following interfaces. It realizes fraud agent, fraud policy, and pattern search. So a component can realize interfaces. What is an interface? Let us review the definition of an interface. An interface is a collection of operations. An interface is a collection of operations that are used to specify the service of a class or component. And when we want to specify that a particular component realizes an interface, we can represent it in this sort of diagram. So this is a component whose name is image.java. And we have another component whose name is component.java. Its name is comp.java. And we have the elided view of an interface here, and the name of the interface is image observer. And we have link between this collaboration, this component, and this realization. So we have a realization relationship here. This is a realization relationship. This component.java realizes the interface image observer, and image.java is dependent upon the interface image observer, which we denote by this dashed line. So this is a realization relationship and this is a dependency relationship. If we wanted to give a more detailed characterization of this interface, we could have written this interface in this manner. So we give the stereotype interface, give the name of the interface, image observer, and specify the operations. Suppose operation is image update, which is a boolean, which returns a boolean. So we have a more detailed specification of an interface, and we can have this components here, component.java, and we can have a realization relationship between from component.java to this interface, and we can have a dependency relationship from image.java to this interface. So interfaces can be either represented in its lighted view like this or in the more detailed view like this. So in the detailed view, we will specify the operations that have to be realized by that interface. So there are two types of interfaces. An interface that a component realizes is called export interface, and an interface that a component uses is called import interface. So export interface is a component that an interface realizes. And it provides it as a service to other components. So the component which realizes the export interface provides it as a service to other components. And import interface is the interface that a component uses. Interface that a component uses is called an import interface, and component conforms to and builds on the import interface. The component conforms to an import interface and builds on it. Component may conform to many import interfaces, and it can also realize and it may provide many export interfaces. Now, the advantage of having this sort of interface is binary replaceability. So you can create a system out of the components, and then you can, and since this components realizes certain interfaces, you can now remove one of the component and replace it by another component which realizes the same interface. So so if you conform to interfaces, you have the advantage of binary replaceability. You can create a system out of components and then evolve the system by adding new components and replacing old ones without the need of rebuilding the system. And interfaces are a key to making that happen. And that is why we say a component is a physical and replaceable part of a system. So component is physical, a component is replaceable, and a component is a part of a system. And it conforms to and provides realization of a set of interfaces. So now we have explained the definition of components. There are two kinds of components. Or rather, there are three kinds of components. One, we have deployment components. Deployment components are the components which are necessary and sufficient to form an executable system, and they consists of the libraries and the executable files. These are components necessary and sufficient to form an executable system. Such as dynamic libraries or DLL files and executables or exe files. The second type of component is work product component. Work product components are residues of the development process, and they consist of files such as source code files, data files, etc. Workflow components are residue of the development process, consisting of source code files, data files, etc. Besides this, we have execution components. And execution components are created as a consequence of an executing system. So they are created by an executing system. Next, having talked about components, next let us define the term deployment. And while talking of deployment, first let us define a node. A node is a physical element that exists at runtime. It's a physical element, it exists at runtime, and it usually represents a computational resource which has some some memory and some processing capability. It represents a computational resource generally having at least some memory and often it also has some processing capability. So you use nodes to model the topology of the hardware on which the system resides, and a node typically represents a processor or a device on which components are executed. Typically represents a processor or a device on which components are deployed. So what is the difference between a node and a component? A node executes components. Components are executed by nodes. A node represents the physical deployment of components, and a node is represented in the following manner. It is represented as a cube, and we write the name of the cube inside it. And we may also write the details. Just as in classes we can write the details, we can give the name and add that this node deploys the following components. So the sales node deploys cost.exe and cont.exe. And then we can show connections between nodes. Association are the most common connections between nodes. Association typically represents a physical connection between nodes. So let us see an example. We have a node kiosk here and a node console. We have a node server and we have a node RAID form. And we have a connection between these nodes, this node and this node. So these three lines denote connections. We can also, along these links, we may denote the type of the connection. For example, this may be a 10T Ethernet. This may be a RS-232 connection, and so on. Next, we define a collaboration. Collaborations are used in the context of a systems architecture, and a collaboration allows you to name a conceptual chunk that encompasses both static and dynamic aspects. So collaborations is a conceptual chunk of the systems architecture. More formally, a collaboration is a society of classes. A collaboration is a society of classes, interfaces, and other elements such as a classifier or an operation such as a classifier. A classifier may include a node, an interface, a component, a class, or a use case, or an operation and is realized by a set of classifiers and associations playing specific roles in a specific way. So a collaboration is a society of classes, interfaces, and other elements such as classifiers or an operation, and is realized by a set of classifiers. A collaboration is a society of classes, interfaces, and other elements and these elements work together to provide a collaborative behavior that is bigger than the sum of its parts. Let me repeat. A collaboration is a society of classes, interfaces, and other elements that work together to provide a collaborative behavior that is bigger than the sum of its parts. A collaboration is also the specification of how an element, such as a classifier or an operation, is realized by a set of classifiers and associations. A collaboration is represented by a dashed oval. For example, this is a collaboration whose name is internode messaging. Collaborations have two aspects, the structural part and the behavioral part. The structural part of a collaboration specifies the classes, interfaces, and other elements, classes, interfaces, etc., that work together to carry out the collaboration. And there is a behavioral part to collaborations. So behavioral part specifies the dynamics of how these elements interact. Dynamics of how and the behavioral part of a collaboration is typically rendered using an interaction diagram such as a sequence diagram or a collaboration diagram. Now about the structural part, within a collaboration, these classifiers may be organized using all the usual UML relationships. The structural part of the collaborations can be organized in a diagram where these are connected with the usual relationships like dependency, generalization, and association relationships. So collaborations actually form a conceptual chunk of the system's architecture. Now about organizing collaborations. There are two kinds of relationships that holds among our collaborations. Relationships concerning collaborations. The first one, number one, the relation concerning collaborations is the relation between the collaboration and the thing it realizes. Relation between a collaboration and the thing it realizes. So it may realize a collaboration, we have already said that a collaboration may realize a classifier or an operation, and we may show the relationship between the collaboration and the classifier or the operation that it realizes. Secondly, we can have relationship among collaborations. Relationship among collaborations. For example, one collaboration may refine another collaboration. and we represent this by using a sort of diagram. So we have here a use case place order. We have a collaboration order management. And this collaboration order management realizes this use case. So this is the realization relationship between this collaboration and this use case. We have another collaboration order validation. And order management, the collaboration order management refines the order validation collaboration. So we have a relationship with stereotype refine. And these two are collaborations. This is a use case. How do we model the realization of a use case? So we will look at the steps that we should follow to model the realization of a use case. Now you will typically drive the analysis of your system by identifying the system. So you start by identifying the system's use cases. Now, after when you turn to implement from in the user requirement analysis part, you will find out the system's use cases. After that, when you turn to implementation, you have to provide a concrete implementation. You have to realize these use cases with concrete structures and behaviors. Realize these use cases using concrete structure and behavior. And now we will show the steps for modeling the realization of use case. Firstly, you identify those structural elements that are necessary and sufficient to carry out the semantics of the use case. Secondly, you need to capture the organization of these structural elements in class diagrams. Capture the structural organization of these elements in class diagrams. Thirdly, you consider the scenarios representing this use case. Consider the scenarios representing this use case. Each scenario represents a particular path through a use case. Fourthly, you capture the dynamics of these scenarios. Capture the dynamics of these scenarios in interaction diagrams. You can use sequence diagrams if you want to emphasize the time ordering of messages, and you can use collaboration diagrams if you want to emphasize the structural organization. Finally, you organize the structural and behavioral elements, organize the structural and behavioral elements as a collaboration that you can connect to, as a collaboration that you can connect to the use case, that you can connect to the use case via realization. Here we will look at an example of a credit card validation system where we have these use cases: place order, generate bill. These are the primary use case. We have one actor, the customer. We have two primary use cases, place order and generate bill. We have two secondary use cases, detect card for fraud and validate transaction, which are included in the place order use case. Now we have a collaboration order management that realizes this place order use case, which is denoted by this arrow. And then we have to now model both the structural and the behavioral aspects of this order management collaboration. The structural aspect of this collaboration will be represented as a class diagram, and the behavioral aspects by some interaction diagram. So we stop here today, and in the next class we will look at the different types of diagrams, implementation diagrams, the component diagram and deployment diagram that are used in architectural modeling. Thank you.